In this video, we shall take a closer look at kinematics. Kinematics refers to motion with constant acceleration. It is constant in time. As time progresses, the acceleration has the same value. That means if we were to plot such an acceleration with respect to time, we would end up with such a graph. Of course, this is assuming that the acceleration is positive. For example, let's say its value is 5 meters per second squared. What that means is the object that is moving with positive 5 meters per second squared acceleration, if the motion is to the right, that means the acceleration is also rightward. So the object speeds up with constant acceleration. On the other hand, acceleration can also be negative. For example, say an object with acceleration minus 2 meters per second squared. That means that the motion of that object is to the right, its acceleration is heading leftward, like that. And in this case, the object will slow down as it moves rightward until it comes to a complete stop. Let's take a closer look at this process. If the acceleration is, let's say, 4 meters per second squared, we just told you the object is speeding up. What does that mean is its velocity, let's say the acceleration is rightward. So the velocity is increasing steadily with respect to time in the same direction. What that means is at t equals to 1 seconds, if the velocity is, let's say, 4 meters per second I hat, at t equals to 2 seconds, its velocity would have increased to 8 meters per second in the same direction. And at t equals to 3 seconds, its velocity now would be 12 meters per second I hat. So if I were to plot v with respect to time, v in the unit of meter per second, t in the unit of seconds, what kind of graph can we anticipate? So at t equals to 1, v is 4, t equals to 2, let's say it's there, v is 8, and t equals to 3, v is 12. As you connect the 3 points, you get a straight line through the origin. Of course, that is assuming at t equals to 0, its speed is 0. The point is, when acceleration is constant, this velocity would change linearly with respect to time. So a general vt graph for a positive acceleration would look something like that. At t equals to 0, let's say the object is moving at some initial speed, you can call that u. Then how do we express v in terms of t? We know from straight line equations, let's say y versus x, and you have a line like that, the general form for y is y equals to mx plus c, where c is the intercept, namely that point, and m is the slope. So in this case, your v is like your y, and your t is like your x. The slope is the acceleration, which in this case is 4, plus u. u is the intercept. So that is the form. Or generally, you can simply write the acceleration as a. So as you can see, this is the first equation of kinematics. What if the acceleration is negative? That means this slope there is a negative number, and vt graph would look something like that. At t equals to 0, let's say it has an initial speed of u. Since the acceleration is negative, the gradient is negative. That means the object is decelerating, namely it's slowing down. So we can simply write it as minus the magnitude of the acceleration t plus u, where in our present case, it is just v equals to minus 4t plus u. What if the graph is like this? It extends beyond that point. What that means is, so you have an object at some point in time, its speed is u to the right, and the acceleration is heading leftward. So what's going to happen to this object? It's going to slow down all the way until it comes to a complete stop. So that means the speed is 0, and that happens there, and it will reverse the direction along the negative x-axis. So that part of that graph explains that part of the motion, where velocities are negative. So in short, the first equation of kinematics is given by this expression. Now let's address the position of the object as it moves along the x-axis. Now we know a is a constant. We know v equals u plus at. Let's take the acceleration to be 4, positive 4 that is. Let's assume that the initial speed is 2 meters per second, so your equation becomes 2 plus 4t. That describes the velocity of this object with time. What can you say about its x-coordinate? How does that change with time? If I were to plot the position of this object with respect to time, this is an xt graph. The gradient of such a graph equals the velocity of the object. Since this is a one-dimensional motion, we can interchange the term velocity and speed, knowing that if speed is positive for the rightward motion, it will be negative for the leftward motion. As you can see from this expression, the velocity is a linear function of time. So that means the gradient of xt graph is a linear function of time. So the xt graph itself must be a curve. So what kind of curve should this be in order its gradient to be a linear function of time? There's only one answer. It should be a quadratic curve. For example, a curve like that. An equation that describes such a curve is quite simply half acceleration t squared. So you see when t is 0, x is 0. The graph passes through the origin. If the kinematics motion has an initial speed to it, then the graph could be something like this. So that means at t equals to 0, the object starts from some point, let's call it minus 2, and at some point in time, let's call it t0, it passes through the origin and then keep moving rightward. So one-dimensionally, the motion looks something like this. At x equals to 2, the motion starts like that. The speed at that time is 2 meters per second. So that is what we call the initial speed. And at t equals to t0, the object passes through the origin and then keep moving to the right. Such an equation can be written in the following form. So this is an equation that describes the position of that object as it moves to the right. Half times the acceleration at squared, in this case the acceleration can be taken to be 4, plus the initial speed, which in our case is 2, you can write it as u t plus the initial position x0. So in this case, a is 4, u is 2 meters per second, and x0 is minus 2. So this is the second equation of kinematics. Sometimes we can write the above equation in a following form: x minus x0. Take this x0 and bring it to the left, and the right side of this equation is simply half at squared plus ut. And the left-hand side, x minus x0, is distance traveled by that object in given time, t seconds. So there we have it, the two equations. The first one is v equals to u plus at. The second one is x minus x0 equals half at squared plus ut. And the third equation we can obtain by eliminating time using these two equations, and the resulting equation is v squared equals u squared plus 2ax minus x naught. These are the three equations of kinematics. Let's look at the following problem. A car starts from rest and accelerates at a rate of 3 meters per second squared in a straight line until its speed reaches 30 meters per second. The car then slows down at a constant rate of 1.5 meters per second squared until it stops. How much time elapses from the start to stop? So let's divide up the motion into A and B. So in region A, it starts from rest and accelerates 3 meters per second squared for some distance, let's call it XA, in time TA, until it reaches 30 meters per second. After that, it slows down with the acceleration of 1.5 meters per second squared, and it comes to a complete stop there. Let's assume the distance is xb, and that is achieved in time tb from that point. So for part A, the time elapses from start to stop is TA plus tb. So let's calculate TA. That can be determined from the first equation of kinematics, v equals to u plus at. So for region A, your v is 30, u is 0, that's that one, the initial speed. Acceleration is 3, t is ta, and you see ta is quite simply 10 seconds. Now let's do for region B. Again, you use v equals to u plus at formula. In this case, the final speed is 0 because it comes to a complete rest there, so 0. U is 30, u is the final speed for region A, plus the acceleration is minus 1.5 tb. And you can solve for tb and you get 20 seconds. So the total time is 10 plus 20. So the answer for part A is 30 seconds. Now let's do part B. How far does the car move from start to stop? So XA plus XB. We are going to assume that it begins at the origin. So the equation of kinematics is x equals to half at squared plus ut plus x naught. But x naught is origin, so that goes to 0. So that means applying that equation to region A, xa equals to half. The acceleration for region A is 3. T is ta, which is 10 squared. U is 0, so plus 0. And the answer is 150 meters. That is XA. Now let's do the same for XB. Using the same equation, the second equation of kinematics, that is, have at squared plus ut. Keep in mind that for region B, x naught is your XA, but x minus XA is XB. And that is given by half. The acceleration is minus 1.5. T is 20 seconds, so 20 squared. U is that 30, so 30 times 20, which will give you 300 meters. So the total distance from start to stop is 150 plus 300, meaning 450 meters. And that solves the problem. As always, thank you for watching.